Can you see my screen? He asks as the inevitable first question.
Yes, we can.
Okay, excellent. All right. Well, I hope you've been enjoying this this Q-Chem segment of the winter school, regardless of the hour. And I'll maybe try and spend roughly the next 30 to 35 minutes just telling you a bit of maybe general stuff about Q-Chem and let you get to know it a bit better, and also give you a little bit of a window into what's new at Q-Chem. In particular, our current release is version 6.1, and I'll be telling you a bit about some of its new features. But first, I thought I would say a little bit about Q-Chem's origins and evolution and history, and a little bit more about how Q-Chem attempts to survive, firstly, and prosper, secondly, in the kind of turbulent sea of competing codes in computational chemistry. And then I'll get to the main part of the talk about new and, well, primarily features that are already in the code. I actually finished up running out of time to make additional slides on the things that are not yet there, but maybe I'll hint at it a bit at least. Okay, so now slightly over 30 years ago, on his Christmas vacation, John Popel's then postdoc, Peter Gill, began to write a new software program with exactly 0 lines of code, and gradually rounded up other contributors. And these days, Q-Chem is governed by a largely academic board of directors, with Hilary Popel being the non-academic financial guiding light for the company. And Anna Krylov is our president, and you can read the names of the others there. You've met almost all of Q-Chem's scientists already at this workshop. There are just 5 of them right now. We fluctuate up and down a bit with time, supported by 2 office staff. And Q-Chem geographically is centered in beautiful Pleasanton, California, part of the San Francisco Bay Area. And from a kind of software development point of view, we consider ourselves to be an open teamware project. And I'll tell you more about developing in Q-Chem later. But if your interests run to development, it's very easy to join Q-Chem's development community, and that's indeed crucial to Q-Chem's survival. We largely prosper as a community project. And over those 32 some years, Q-Chem has grown from 0 lines of code to something like 8 million lines of code, primarily C++ these days, but there is still legacy code, including code written by the wonderful Nobel laureate John Popel, who was my own PhD advisor a long time ago. You can see the JAP 12/02 comment in this piece of legacy code. Starting up Q-Chem led to some side effects. So in particular, I and various others had a very nasty sort of software divorce with the Gaussian company. So I'm a founding member of the Banned by Gaussian Club, and we don't have membership cards or anything, but I have vivid memories of how that happened. So today, Q-Chem is the sort of most recent publication describing Q-Chem is this sort of magnum opus in the Journal of Chemical Physics, whose authors largely fill a screen. And the point here really is that building an 8 million line code is truly a community effort. And so these people constitute our community at the snapshot, the moment of writing in 2021, as well as a kind of a tradition we have for recognizing earlier contributions for a well-defined period. Okay, so then the contributors are indeed Q-Chem's main office, and a function of the main office is really to enable scientists in academic collaborating groups to do their science. And so the Q-Chem office coordinates distribution, it manages user support. It also, the office also manages and maintains a framework for decentralized development. as well as a thoroughly meritocratic process for committing code. Namely, if your code can pass our regression tests, it will be committed. And the office, our scientists work on critical software infrastructure. You'll see some of their recent accomplishments later on in the new features part of the talk. And managing an 8 million line code also means grappling with legacy as well as modernization. And the office tends to lead initiatives within our community to modernize our code. And despite being an object-oriented code where C++ has been in use since the late 1990s, bits of the code are always going out of date, and it's really a crucial function of the office to manage code modernization and infrastructure reform and development. And then our academic developers are on the order of 20 fully committed groups, a number of whom are represented here, and roughly another 20 loosely associated groups. And with the office, Q-Chem's central office taking care of the activities I mentioned, the academic contributors and collaborators have the opportunity to innovate, and innovate. And the idea is basically, use Q-Chem as a software platform to try and do new things, and also be responsible community members. So don't check in half-written code, and occasionally, if you feel that you can justify it, then help with fixing bugs and modernizing code and building infrastructure. And so you can really see that in some sense, Q-Chem's got two classes of customers. There are the end users who buy Q-Chem to run jobs and do projects. And then there are the developers who buy Q-Chem to get the support of our community and our full-time employees in particular to enable their science. And so roughly that's how Q-Chem works. And in terms of then the product of groups times group members, we have more than 100 active developers. And when I checked last night, Q-Chem papers have been cited over 700 times since the beginning of 2023. And this is just indicating where the development groups currently are. And you can see some noticeable gaps, but certainly North America, Europe, Asia, and Australia are represented. So Q-Chem is a commercial code because we take the view that essentially governments pay with their research dollars for the development of new science in computational quantum chemistry. But just as people who run quantum chemistry codes to solve chemical problems buy their own computers, we feel they should also contribute to software sustainability by buying a code. So we don't sell our code for very much money. It's very cheap compared to even a single node of a computer system. But this is our view of sustainability, and Q-Chem has sustained its code for over 3 decades. So our model has been successful so far. We're also well aware that even modest license fees are painful for some people, so we try to make sure there is always free access, and we have 2 modes of free access. We firstly provide Q-Chem at no cost to supercomputer facilities that are national or that don't screen applicants based on any arbitrary criteria. And Q-Chem itself runs a small-scale server for teaching purposes and trial purposes. And so typically, users interact with Q-Chem the way you guys have been, IQML, but you might also use direct scripts or another interface, or maybe even the cloud, as we'll talk about in a minute. And then, consistent with the fact that we really have 2 kinds of customers, a development license costs nothing different than an end-use license, because really we want to encourage people to develop in Q-Chem, and we want to provide the support and long-term sustainability that's necessary to make a code thrive and a community firstly survive and secondly prosper. And thus this no-cost development license is really our way of saying there's an open invitation to join us. And we don't insist on software exclusivity. So a developer in Q-Chem can even put their code into an open source code as well, or in principle, even contribute to a different commercial code. I don't need to say much about IQMOL because you've all been using it, and it's basically, if you download it, you may well have been running your jobs on the Q-Chem server as is, and that's something that gives you full access to Q-Chem functionality just in a time-limited way, and we view it as sort of a low barrier entry point for testing, evaluating the software, and also for teaching. Well, going through all of Q-Chem's features would take ages, so I'm not going to do it, but this is sort of the handy one-slide summary of areas of strength for Q-Chem, which is, it's essentially a fully molecular code these days. One of our ongoing research projects is to have a solid, condensed phase periodic boundary condition variant of Q-Chem, that is QC-PBC, that's under development. But we have an enormous array of density functionals, wave function methods, and analysis tools for the ground state. We have a comparable set for excited states. We have an array of methods to allow you to walk on potential energy surfaces, some of which are unique to Q-Chem, some of which are relatively standard across quantum chemistry codes. Likewise, the treatment of implicit solvent or explicit solvent through QMMM or density embedding is something all state-of-the-art quantum chemistry codes need to have, and Q-Chem is no exception. And then there's a bunch of other special features that also exist. All right, so that's kind of the broad overview, and I should say that, again, the community notion means that we can't necessarily do everything ourselves. It's an open question what the future of GPUs is, but Q-Chem has partnered with a Hungarian company, Brian QC, and we have a joint Q-Chem Brian QC GPU product that is available for people who have high-performance GPUs. We have also partnered for a long time with Wavefunction, a computational chemistry visualization software company that makes the very, very widely used Spartan codes. Spartan 24 is very freshly released, and its back end is Q-Chem. And that's another way of using Q-Chem itself. And then we also partner with WebMO as an alternate interface. Various ways to extend the core functionality of Q-Chem. All right, so that's the end of part one of my talk. Now, part two is really to take a sort of a stroll, or sort of something like a bus tour, maybe, alighting every so often to look at something and hopefully appreciate something neat about it. And I'll range from kind of new science features through to core performance, and then wrap up with a brief outlook. One thing that the Q-Chem office has put major effort into, and it is now, as I understand it, complete and ready to roll, is the Q-Cloud product, which is then a way of avoiding the need to buy hardware in order to use Q-Chem. And instead you can set up instances of Q-Chem jobs on Amazon Web Servers, elastic compute clusters, and we've done everything necessary to make that as straightforward, seamless, and painless as possible. And in particular, you get the benefits of cloud computing this way, which is you may have a short but intense need to run lots of jobs for an urgent project, and then maybe no such urgent need for the next few months. And so cloud computing lets you flexibly scale resources up and down as needed. And that's really the mode in which it's optimal. You also don't need to manage your on-site computing. And in principle, there may be higher energy efficiency as well. So Q-Cloud is brand new, and may well be the way things go in the future. At my own university, we are out of space and out of energy capacity, and so our own servers are being relocated to another state, very likely. And so the logical step beyond that is to go fully cloud-based. I don't have time to talk all about Q-Chem's spectroscopy capabilities, but they span at least 7 different areas of spectroscopy, and I'll just highlight a few recent developments that are new features. One that is due to Kuan Yu, who you've all met. I think he's at the workshop. He's developed this in partnership with a previous employee, Yu, and vibrational circular dichroism with density functional theory is now available in Q-Chem in 6.1, with the unrestricted version coming soon, the restricted version available now. And well, it has major uses in terms of small organics and essentially stereochemistry and chiral molecular structures, natural products, and so forth, and drugs where you want a specific stereoisomer are examples of VCD applications. Q-Chem has a long, strong tradition in couple cluster theory that is really led by Q-Chem's president, Anna Krylov, and her group has continued to be the main lead in new couple cluster features, but now others are coming from newer development groups such as Thomas Yago's group, and this is a little catalog of new couple cluster features, which include ECD and optical rotation at the couple cluster level. Anna's group has worked intensively on core spectroscopies for the past decade or so, and Auger decay is now featured, and then complex valued CC2 and CCSD come from Thomas Yago's group, building on earlier work from my group, and also some new CC2 capabilities, and even CCSD full T energies. So lots and lots of couple cluster capabilities. This really just more or less scratches the surface, I would say. Another project which has been largely done at the office, and this is built on code that came from Wanzhen Liang's group in Xiamen in China, and has been adapted by our office staff, is to do full visualization of full Frank Condon analysis of electronic spectra to see line shapes associated with vibrational transitions. And so if UV vis spectroscopy is your thing, then this is a very nice addition to Q-Chem that is now controlled through IQMO. More on the theory side, and this is a project my group has completed recently, is a unique development in time-dependent density functional theory for X-ray spectroscopy for core excitations. And the kind of scientific motivation is that orbital relaxation is crucial to describe a core excitation. So suppose you're exciting from the 1s orbital in water into something like a Rydberg or sigma star orbital. Well, upon making the hole in the 1s orbital, you've effectively changed the atomic numbers from an oxygen nucleus to a fluorine nucleus, because you've lost an inner electron. So screening is reduced. All the other orbitals should contract towards the nucleus as a result of that core hole appearing. But that crucial orbital relaxation is entirely missing in TDDFT, which then is one of the 2 factors leading to large errors in TDDFT for core excitations. And in a nod to something that came out with Q-Chem version 6, is that Q-Chem has great orbital optimized density functional theory capabilities that relax orbitals and do one state at a time. TDDFT gets you all the states in one shot, so it's tempting to ask, can you capture the orbital relaxation effect in TDDFT? And conventionally, the answer is no. But if you do an unorthodox form of the theory, which is a double response theory, beginning from the ionized, the core hole ion, then reattaching an electron first back into the hole level, and then making a hole to particle excitation, then in fact one can consistently include orbital relaxation because TDDFT is being done with ion orbitals, but additionally with the correct exchange correlation kernel. And the proof is in the pudding, as they say. So, so for 120 K-edge excitations, for a variety of functionals, everything from the Hartree-Fock functional to the standard BLIP and SCAN through to range-separated hybrids. Here is data in pink for conventional TDDFT and in blue for EA TDDFT. And you can see there is an enormous improvement in the RMS error, falling from up as big as tens of electron volts down to, in some cases, less than 1 electron volt as a result of taking care of the orbital relaxation effect within TDDFT theory. And well, you can maybe see a few things here. It looks as though there is less sensitivity of the EA TDDFT errors to the choice of functional than there is in the TDDFT errors. The bottom panel, by the way, is then the blow up of the EA TDDFT error statistics. And when you look at it closely, it's this functional over here, RCAM B3-LIP, which on this data set is slightly the best. Omega B97M-V is also very good. And there are a few others that are pretty decent as well. But EA TDDFT is only available in Q-Chem. And if you're in the business of computing core spectra, it's an inexpensive and powerful way to greatly improve your results. Speaking of inexpensive and powerful, DFT is what almost everybody runs, almost all of the time. So we should spend a little bit of time talking about Q-Chem's DFT performance and how it looks on medium to large size systems. So here is a medium to large size system of about 250 atoms, 128 heavy atoms, in a basis set big enough to be respectable. So that's more than 47, 48 basis functions down here. And the plot is wall time in seconds against the number of cores used to run the job. And the basic point is that, you know, an hour is 3,600 seconds. So the standard SCF features very good parallel scaling out to about 32 cores. So essentially on a modern node like an AMD EPYC Milan, you are then looking at time to solution of, you know, less than half an hour for nearly 5,000 basis function SCF, which is really cool, and good parallel efficiency, so we're not being wasteful of energy. If we then ask, well, can we do better? Q-Chem does have nice RISCF code, and this is primarily thanks to Xintian Feng at the office, our lead scientist in Pleasanton. And so for the same job, same functional, the same basis set, the RISCF times give you a speed up of close to an additional factor of 2 here. A meta GGA like TPSS has a fairly heavy exchange correlation component to the calculation, but the speed ups are nonetheless very good by doing RI, which helps with the Coulomb piece. And in a Q-Chem input file, it's just a matter of basically adding one more line to the input file to say, oh, yes, Q-Chem, I would like an auxiliary basis for the J term, the Coulomb term. So yeah, so that looks really, really nice. And then maybe it's worth saying that you can never be too rich, too thin, or run too big a basis set. So so here are some results in DEF2 QZV-PP. So quadruple zeta. This is a slightly smaller system, but still 117 atoms, 61 heavy atoms. This is slightly over 5,000 basis functions, and the numbers in red are without RI. Again, you see the good parallel scaling, and with Ri are the numbers in green, in sea green, and you can see a really very big speed up. And this is a consequence of the OC-RIK algorithm, which was one of my inventions a while ago and has now been very, very well optimized in Q-Chem, including parallel scaling, such that you can enjoy these very, very big speed ups when you run large basis sets. And again, from the input perspective, you're just adding one more line to the input to say, I would like an auxiliary basis for the K matrix as well. Anyway, so that's core density functional theory performance, and it looks really good on sort of medium scale parallelism. Q-Chem is not a massively parallel code, although we have projects that are pushing more in that direction that are going on in background. Speaking of DFT, there are things you can there are many things you can do in Q-Chem that you can't do in other codes. And amongst the very best functionals are the VV10 corrected combinatorially designed density functionals from my group about 5 years ago with my wonderful former graduate student Nabe Marderosian. And with a wonderful present graduate student, Jiaoshu Liang, and the wonderful Xintian Feng from Q-Chem, we have implemented for the first time anywhere in any code the analytic Hessian of VV10 as needed to do analytic frequencies, for instance, with omega B97 X-V or M-V. And there are efficiency advantages in terms of speedups. And there are also precision advantages. You don't want to do finite differences unless you have to. And furthermore, given Xintian's focus on parallel scaling, he and Jiaoshu have worked on this as well, and the new code also achieves slightly over 80% efficiency out to 32 cores. So this is a desirable feature that you can only get in Q-Chem. Another distinctive feature in Q-Chem that comes from a German development group, the group of Tim Neudecker in Bremen, is quantum mechanochemistry. In other words, modeling molecules under applied strain or applied pressure. So essentially, Tim's group has implemented a range of models, culminating with their ghost ship model, and these are valuable for modeling experiments such as single molecule force spectroscopy, so pulling experiments, or sonochemistry, which is transient high pressure, or nanoparticle synthesis, which can occur under changing pressure conditions as well. So if one wants to explore how the energy as well as all properties of molecules respond to pressure, Q-Chem's got something that can do it for you. You have just finished the segment of the workshop on energy decomposition analysis, and these are tools that were largely originated in my group, and I continue to have a great interest in EDA development because I feel it's an underexplored area of quantum chemistry. And one project that we have just finished in collaboration with UEGI, as well as Pedro Salvador and others, Teresa's group as well, is force decomposition analysis. So if you can decompose an interaction energy, you can also take the full geometric derivative of the interaction energy to make an interaction force, and then break that into components. And you'll get a preparation force that describes any geometric distortion and electronic if pertinent. Then a frozen force that captures the standard frozen effects of permanent electrostatics, dispersion, and Pauli repulsion. The gradient of that was non-trivial to implement, as Abdul can tell you himself. Then a polarization force, that's considerably easier because the polarization energy, while constrained SCF, it's variationally optimized. And then finally, just by subtraction, charge transfer forces. And then you can begin to ask questions like, well, what is this good for? I think it's good for a lot of things, actually, but let's just take one example. Here is force decomposition analysis for the chloride water system, which I think is what you guys might have just been looking at for EDA. And the point here is that we chose the water molecule at its optimized gas phase geometry, and that means there is no preparation force. In other words, the water molecule starts off in the geometry it wants to be by itself. But now let's look at how things go when we then take the gas phase geometry of water and we optimize the position of chloride relative to it. So between the proton donor and the chloride, that's an optimized distance. So we get perfect force balance. So what you're looking at here on the y-axis are positive forces that want to push the atoms further apart, and negative forces, attractive ones, that want to pull them closer together. And intuitively, the repulsive force is entirely Pauli derived, and the attractive forces come from everything else. From everything else, and in particular, charge transfer, the polarization, and the electrostatics all would like to make the distance shorter. Then it's kind of interesting to look at the unbalanced. So that's a case where the forces are in balance. What if the forces are unbalanced? How about the oxygen proton donor distance here? Well, all the forces there point in the same direction. All components, the electrostatics, the van der Waals, the polarization, and finally the charge transfer, they all want to elongate that bond, consistent with a small amount of electron donation into it, as well as accommodating the changed electrostatic environment and everything. Anyway, so that's sort of what you can see. So there is a role for charge transfer in the intermolecular force balance. So people who think that the hydrogen bond is just an electrostatic thing, it's not entirely true, but neither is it entirely a resonance phenomena. This is the kind of force fingerprint of the balance. And then in the intramolecular proton donor chloride distance, you can see a synergistic effect where all components want to point the same way. Another new thing in Q-Chem around energy decomposition analysis is to analyze the polarization term. We already have had for a couple of years analysis of the charge transfer terms that gives you the main donor and acceptor orbitals. But if you go from the frozen wave function, say lambda equals 0, to the polarized wave function at lambda equals 1, we now have theory and an implementation that gives you an exact breakdown of the contributions of the polarization energy in terms of orbitals. Orbitals that become deoccupied partially, or if they're occupied, or partially occupied if they're virtual. And this lets one see the dominant contribution, the main physical drivers of polarization in a given system. So let's take a look at the water dimer, the humble water dimer. The biggest polarization effect is on the Lewis base, this water, the right-hand water. And what you're looking at is, in bold, is the occupied orbital, and in hashed, cross-hatched, is the virtual orbital. So we are seeing essentially and the phase is significant. This is essentially polarizing the oxygen lone pair in the direction of the proton. And that accounts for 60% of the polarization interaction. Another 20% of the polarization comes from is on the other fragment. So remember, polarization is on a fragment, not between fragments. It's the polarization on a fragment due to the other. So here the occupied orbital is evidently the OH sigma orbital on the proton donor water. And the phases are significant. So this red crossed hatch means destructive interference. It means that the sigma orbital is retreating away from the incoming Lewis base. And that looks like a relief of Pauli repulsions more than an electrostatic polarization. Anyway, it's very interesting. It's or from an electrostatic point of view, maybe we can say it's inducing a larger bond dipole by the OH sigma bond retreating away. Anyway, you can read about it in this paper, and more importantly, you can run it in Q-Chem. Okay, so I'm going to wrap up here because I'm supposed to join another meeting in 4 minutes. So time's a little delicate, but here's how to learn more. Visit the website, watch our many webinars, browse the online manual, and also keep your ears peeled and eyes open for new developments, because we do have a bunch of them, a lot of exciting things going on. I foreshadowed a periodic boundary condition effort that is at an early stage, an early but not beginning stage of development. It's already running. There's also an advanced molecular mechanics project led by Teresa Head-Gordon, M-Chem, that is likewise not yet really ready for distribution, but is underway. So there's exciting stuff coming there. And then there's lots of exciting additions to the core capabilities. I don't have time to tell you about new linear scaling work from my group, but we're very excited about that. Lots of stuff going on. If you are interested, or if you want to inquire about getting a license for Q-Chem, there's forms on the website, there's people you can email. And if you are running Q-Chem or have questions about running it, there's a Q-Chem forum. And we do participate in the usual social media suspects. And let me thank the Q-Chem team. We are immensely grateful to everyone who's able to help us sustain this project and make it the community it is today. Also the Q-Chem board members, especially Anna Krylov. Being president of Q-Chem is a slightly thankless task, and so we all owe Anna great thanks for her leadership, and everyone on the board pulls together to try and make things happen. And that's making things happen is particularly true in the Q-Chem development community. So I want to thank everyone who develops and contributes code. And finally, I'd like to thank you for listening, and I can take a question or two if there are any, and I'll stop there.